Hello, welcome to Pre-Calculus. Today we're going to be covering combining polynomials, so put away those distractions, pull out those notes, and here we go. Today we're talking, like I said, about combining polynomials. As you can see, all the things we'll be discussing is in purple. The kind of bluish words let you know, hey, combining monomials is sometimes also known as exponent laws, combining like terms, or possibly even distribution. So, let's get going. Before we can define a polynomial, we have to define a monomial. So what is a monomial? A monomial is a constant, a variable, or the product of constants and variables. So what exactly does that look like? Well, first off, constants are those wonderful, delightful numbers you got to play with back in elementary school. Things like 5, 207, -31, our good friend pi, and even his lesser known cousin e. These are all constants. They have specific values that we know what they are. Now, along came algebra, and we got introduced to variables. Variables are things that we don't actually know what the specific value is for it, because they vary. And those classic examples from algebra include x, y, and z. Let's make a little bit better z. There we go. X, y, and z. Geometry introduced us to things like A, B, C, and other various things. My favorite ones, though, are the ones that aren't necessarily letters. You can use question mark, you can use box, you can use dead face, bleh. Or maybe it's a good day, happy face. As we're going along, we're mainly going to be using X, Y, Z, and we'll also be introducing variables in the form of the Greek alphabet. The most popular one is theta, which is a circle with a line through it, and his good cousin phi. So those are some examples of Greek letters that are coming very soon to a classroom near you. Last but not least, we have the product of numbers and variables. Mrs. Norton, what the mess is a product? It's been a long summer. I have no idea what that means. Product is also known as the answer in multiplication. So when we multiply two numbers together, the answer that we get is called the product. So multiplication, there we go. So basically what that means is we're going to take numbers and variables and we're just going to smush them. Floop. Typically a monomial only has one number and then it'll have letters. Boop, boop. Or maybe pi r squared or 2/3 pi. Or yeah, 2/3 theta. Those are all good examples of monomials that we can use in polynomials. So polynomials are the sum or difference of monomials. So we can, Miss Norton, there's those fancy dancy words again. What do those mean? So as a quick little reminder, if I can get my thing to cooperate with me, a sum is the answer in addition. And the difference is the answer in subtraction. So basically what we're going to be doing is we're going to be taking various monomials and we will be adding and subtracting them together. So if we took our wonderful thing that we've got set up here, we have 5xyz squared minus pi r squared plus 2/3 pi. That is a polynomial, a very disgusting polynomial. Most of the polynomials in this class, I go so far as like 95 to 99% of them are just going to utilize one variable at a time. So they might look like 15x squared minus 37x plus 9. That's a good little polynomial. You might also see something like 42 u to the 4th plus 78 u squared minus 5. Another good example of a polynomial. So those are the types of things you're going to be seeing. Now, each of these individual terms are the different monomials that make up a polynomial. And so it's important to be able to talk about, okay, so what are terms when we're talking about polynomials? And so let's take a look at this guy, and we'll take a look at that guy. So first up, we have our 15x squared minus 37x plus 9. And so we need to look at each of the individual monomials. So that would give us 15x squared. That's my first monomial. My second monomial is minus 37x. And last but not least, we have positive 9. Miss Norton, why didn't you write plus 9? Well, because it's assumed things are positive if there is no sign. If there is no sign, it's a positive. If there is a sign, it's a negative. And that's just kind of how a lot of people actually go through life. Anyway, our other polynomial has 3 monomials as well. We have 42 u to the 4th, we have 78 u squared, and we have negative 5. Can all of the terms be negative? Of course. All of the terms be positive? Definitely. It doesn't really matter. Degree of the term. Now, the exponent or some of the exponents in that particular term. So, if we were looking at our orange guy, we have our terms 15x squared, negative 37x, and 9. Now, fun fact, I don't care about the numbers on these really at all. I just care about what the exponent is. So the exponent is squared, the exponent is to the 1. What is this one? We'll have to talk about that later. Then we've got this guy. He's got 42 u to the 4th. He's got 78 u squared. He's got negative 5. Again, I don't really care about the number bits, but I do care about this gives me an exponent of 4. This gives me an exponent. I do not know why that turned into a plus sign. Let's try that again. 2. And this is our mysterious what the mess is going on. And let's take this other guy up here, because he's got some useful, oh my goodness, that's really big. Let's try making that smaller. There we go. We got 5xyz squared. I want to look at that particular one right there real quick, because again, we don't care about the 5. That's the constant part of this monomial. We do want to care about the exponents. So this is really x to the 1, y to the 1, z squared. So that's 1 plus 1 plus 2, which gives me 4. Floop. That is the degree of this particular term. Last but not least, we have the degree of the polynomial. How do we determine the degree of a polynomial? Well, we just look at the degree of each of the individual terms and we grab the biggest number. So if we were going to look at our little orange dude here, our biggest polynomial is, our biggest term for our degree is 2. So that makes it the degree of the polynomial, or 1, or the I don't know. And then we've got our, I should be using different symbols. Anyway, we can do 4 or 2 or I don't know. So 4 is our biggest. And for the red guy, up there. Yeah, actually this is our biggest term. It's 4. This guy has a degree of 2. And this guy has a degree of 1. So yeah, 4, 2, 1. Boop. That is our degree for this polynomial. All right, we're about 8 minutes in. This is a great spot to stand up, stretch. Actually, wait, you're about to fill in a chart. Never mind. Turn over your page. Let's start filling, or go to the bottom of the page. Let's start filling in charts. Yay, charts. Oh, it's so exciting. Okay, this is a great time to pause the video and just fill that in real quick. Yep, now, good, got it, sweet. Now pause the video again, and just, there you go. Pause it here, and fill this part in too. All right, now let's talk about it. Okay, so we can classify polynomials in 2 different ways. We can classify them by their degree, which is the number of monomials that the degree, which is the exponents. We just got done talking about degrees. So if something has is no degree, it is called a constant. So if we went back over there where we had like the 9, that's a constant, 17, 25, those are all called constants and they have a degree of 0. So we can sneak back over here real quick. And this is actually a 0. Just real quick. Up here. All right, we can have linear, which means that, we'll think of like linear functions. We have a degree of 1, so 3x plus 7. Quadratics, cubic, quartic, quintic. Typically speaking, we don't really go after quintic. And then we also classify by the number of terms. If there is no term, like there is right here, there's nothing there, so we don't have a polynomial, so we're not classifying the polynomial because there's nothing. If we have 1 term, we already talked about that, his name is monomial. If we have 2 terms, his name is binomial. 3 terms is trinomial. And after that, we just call them polynomials. We don't call them quadrinomial, blah, blah, blah. So let's do some quick examples, just really, really quickly. Excuse me, I don't want to use pink. There we go. let's say we have 3x minus 7, so that would be linear, because my biggest exponent is 1, and it would be a binomial, because there's 2 of them. Alright, we could also do something like x to the 5th, and that would be quintic, and it would be a monomial. Kind of makes sense? Pretty straightforward. Classifying them, not too terribly crazy. You just look at the 2 different things. We can do 3x to the 5th minus 74x cubed plus 17x to the 7th. Oops. That would be whatever the 7th one is. I should not have done that. We'll do squared. That's boring. Anyway, quintic. And this is a trinomial. Doop-a-doop. Trinomial. There we go. Beautiful. Alright, now is a good place to stop, stretch, get some wiggles out. We're about halfway through. Alright. Alright, so now we are going to be talking about the chart on the next page. Yay, so many charts. Awesome. So now we're going to be talking about how we combine monomials. Specifically using exponent laws is kind of where we're focusing in on this first bit. So when we have exponent laws, we have these various different things, and we're going to be talking through a couple different examples. So the product rule is when we have the bases are the same, and we're multiplying them together. What do we do with the exponents? Well, we add the exponents. So if we had x squared times x cubed, that would be x squared plus 2 plus 3, which is x to the 5th. If you on homework want to go straight from here to there, that's perfectly a-okay. Just trying to show all of the steps as I'm going along. If you have something to the exponent to another exponent, so with parentheses are always involved in this case, and you got exponent to exponent, then that means you're going to multiply those exponents together, and that will give you x to the 6th. Really quick fun fact, we will never, ever, 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 for this class, use this as a multiplication. That's not multiplication. This is a variable, not a symbol. No more. No. If you want to say that 2 things are getting multiplied, you're going to use the dot, or you're going to use parentheses. This is how we signify multiplication in pre-calculus. The x is no longer a symbol of multiplication. Anyway, there's that one time, but we'll talk about that when we get there. Quotient rules is when we're used to do subtraction. So let's say we have x to the 5th over x squared. Then we would do x to the 5 minus 2, which would give us x cubed. And our good friend negative exponents just means, so a lot of people think of negative exponents as flipping. The official term is reciprocal. And what that would mean is that you move it down to the bottom. And this is kind of your classic example. I want to do a couple of others just because it's good to see them. If you have 1 over x, well, let's say 10 over x to the negative 3, that would become 10x cubed, technically over 1, but typically we kind of ignore the over 1 part because we understand that that's there even though we don't always write it down. Another way that sometimes gets people a little confused is if you have like x to the negative 3 over y to the negative 2 with the, let's throw a z up there, and 7 down here. So the x would move, oh snap, I'm just going to do this later. The z and the 7 stay still, x cubed comes here, y squared goes there, and everybody's all happy, hunky-dory. Next, last but not least on your, next we've got the 0 exponent rule, which basically states that anything raised to the power of 0 is just 1. So if I take 2075 x to the 27 and I raise that to the power of 0, that just gives me 1. And that's actually where this constant idea comes from. So technically, would you agree that if I multiply something by 1, I just get that number, right? And x to the 0 is just 1. So technically, 9 is really 9 times x to the 0, because that's where the exponent is, and that's how we get the degree 0 is constant, it is a legit degree, it is actually a monomial. They all have variables in them. Some of them are just raised to the power of 0 and you can't see them. So anyway, fun fact. Distribution rule. I call this the distribution rule because I can't think of another name of it for it. It is not actually distribution. It's spreading. It's like spreading it out like jam, like distribution does. Anyway, if you have a couple of things inside parentheses, so let's say we have 3x squared and we're cubing that sucker, that would mean that we need to cube each of the individual things within the parentheses. So that gives me 9x to the 6. All right, so let's bring them all together, bippity boppity boo, into a wonderful, glorious example. Yeah, we're gonna have some fun with this. So we're gonna have 39 c to the 7 c to the 4th over 24 c squared d to the 7. And we're going to square this whole thing. Bada bing, bada boom. And our directions are going to say something like simplify the following expression. And that's how we're going to do it. So how do we do this? Where do we even start? So typically speaking, what I do is I start by finding the letters. This isn't showing up quite as well. This one? That shows up better. So I find the numbers, right? And I put them down. 39 over 24. And I simplify that. That's 3 times 13, 3 times 8. And the 3's cancel, which gives me 13 over 8 for my number bit. All right. So I've got 13 over 8. All right. Next up, let's see, does the yellow show up? Oh, yeah, the yellow shows up. Let's grab all of the C's, because that's my next letter. I usually go alphabetical order, A, B, C, D, E, F, G. I don't have any A's or B's, but I do have C's. So I've got C to the 7, C to the 4 over C squared. So let's see, my exponent rules say add the ones on the top, and then subtract what I've got top and bottom. And so that guy technically goes on the top. There we go. And then last but not least, so see D, here's my last guy. And fun fact, there's no other D's. So he just gets to stay exactly precisely where he is, as he is, and he doesn't get to do anything else, and it's kind of fun. But why are there still parentheses? Because there was this little squared guy out here, which means all 4 of those things inside need to get squared. 13 squared, c to the, that looks tongue-tied, c to the 9 squared over 8 squared, d to the 7 squared. Everything inside the parentheses gets squared. So that gives us 169, c to the 18, 64, d to the 14, and I can stop there. I know the numbers are relatively prime because we already simplified them down first, so I don't have to check it to see if 169 and 64 have anything in common. Whew, we made it. All right, now we're going to talk about combining polynomials, adding and subtraction, addition, subtraction. We're going to combine like terms. So here we go. Going to pull up, make sure I do the right example. So when we're adding and subtracting polynomials, what we usually like to do is we'll list out the one polynomial inside parentheses, so b squared plus 5b minus 11, and we'll list out the other set of the polynomial, so 8b squared minus 2b minus 7. Adding these would just be really, really lazy and a little too easy. You just find all the like terms. No. We need to talk about subtraction. So we're going to jump straight up to level 2 and kind of skip over level 1. If you don't remember how to level 1, go consult your algebra. So what we're going to do is we're going to distribute this negative to each of these duders over here. So we're going to change all of their signs. So we have negative 8b squared, positive 2b, and positive 7. Now we go looking for like terms. So we've got, here's a b squared, here's a b squared. So we have b squared minus 8b squared. That's going to give me negative 7b squared. You do not have to go through and show all of this level of work. I just am because it's a habit. So that would give me b7b, and this guy with this guy, negative 11 plus 7 would be negative 4. So my final answer is negative 7b squared plus 7b minus 4. Boop. Bada bing, bada boom. Bada bing, bada boom, boom, boom. All right. Combining like terms, easy peasy. Nice and breezy. All right, let's try multiplying, because that's where the fun is. Yeah, multiplying, yeah. So once again, we're going to write out our polynomials, or we're going to have parentheses. So we're going to keep it like kind of level 1 first. We're going to have x as our first polynomial, and 3x squared minus 7x as the second polynomial. distribution says we're going to take this guy, we're going to multiply him to both of those guys inside. So we have x times 3x squared. And then technically it's plus x times negative 7x. Technically, officially speaking, a lot of times what you'll see people do is they'll write this as negative x times 7x. It doesn't really matter which way you write it, you end up getting the same answer either way. So now that we have to do this distribution anytime that we have a positive or a negative, anytime we don't have a monomial times a monomial. Monomial times monomial, we go back and play with exponent laws. If we have a monomial times a bi, tri, poly, anything else, or anything, as soon as we aren't just playing with monomials, we have to pull in these this distribution. So, yeah, anyway, let's going along sing a song. We end up with 3x cubed, because now we do have monomial times monomial, so we're going to use our good old polynomial rules with our exponents. Alright, bada bing, bada boom, that's done. Yeah, but that was like level 1. Let's try, oh, we can do it. Getting close to the end of time. Let's do it. Binomial times a binomial. This is kind of like the bread and butter of like algebra 2. This happens all the time. And so for this one, you see people will say FOIL when they see these. I personally don't like FOIL because it doesn't work when we get to our next level, and I'm going to show you why. So first off, what we're going to do is we're going to take this guy and we're going to multiply him by that entire second polynomial. And then we're going to take this guy and we're going to multiply him by that entire second polynomial, like that. And now we're going to go back to what we did the last time, which is where we did our bippity boppity boo and shoved the thing in. So doodaloo and doodaloo. So that gives me x squared minus 7x minus 5x plus 35. And final answer is x squared minus 12x plus 35. Okay. So, FOIL if you want to do, but this works all the time, and foiling doesn't work all the time. It's very, very sad. So let's, sorry, change the tab I was on. Let's look at something a little more complicated, a little bit more fun. Yeah. This is probably as complicated as I'm going to make them on the homework, which is sad because we can totally go trinomial times trinomial, and it's so much fun. But I've learned that for some reason students don't always find things to be as enjoyable as I do. So we're going to take this guy as our first one, and we're going to do this guy for our second, and I'm just going to kind of underline this whole thing in blue. So we're going to have x, 2x squared plus 6x minus 7, and then we have minus 3, and then you've got 2x squared plus 6x minus 7. Boop, 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 doo, 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 doo. Sorry. I really, really like multiplying and distribution. It's fun stuff. Okay, let's go. And 2x cubed plus 6x squared minus 7x minus 6x squared minus 18x plus 21. Okay, so there's that blastedness of redness. We're going to look for like terms. There's 2x cubed squared, 2x cubed, and then we've got a squared and another oh, they cancel each other out. Oh, that's glorious. I love it when that happens. And then an x and an x. Those are both negative. So that's going to become negative 7 minus 18. So, change colors, you turd. Minus 25x. And then, last but not least, plus 21. Boop, boop, boop. All right, there we go. Let me know if you have any questions, concerns, comments, or queries. Miss Norton, you talked about addition and subtraction. We talked about multiplication. What about dividing? We're going to talk about combining things through dividing? No, we're not. No, not right now. Like, give it a couple months and we'll get there, but that's uber complicated. No. Our next video is going to be about factoring. Please don't forget to fill out your video reflection. Go back over your notes, make sure everything actually makes sense. If it doesn't, go back and like cherry pick through the video. And again, fill out the video reflection. Please let me know what questions, concerns, comments, or queries that you have. And happy mathing!